in order to see the derivative of the wave function or wave equation. So in the previous video we saw that the equation of the mathematical equation of the wave was g as a function of x and time is equal to a times the cosine of x, of a constant number kx minus omega t. Now first, let's take the partial derivatives. So what is the first partial derivative of y of xt with respect to time? This would be, we would hold x as a constant and we would just have, this is very easy, it would be a cosine, or, it would be minus omega times, the a minus sine, so plus sine of kx minus omega theta. So this is the first derivative. Now let's do the second partial derivative of y of xt with respect to time. This would be now minus omega square a cosine of kx minus omega theta t. So this is the second partial derivative. This is the second partial derivative of y with respect to time. If this was the displacement, y, remember, was the displacement of the particles, then this is the velocity and this is the acceleration. So this is acceleration on the y axis. So acceleration to y. Now let's take the partial derivatives of y with respect to x. So now we have the partial derivative of y of xt with respect to x. So now we are holding this as a constant, so we just have minus k a cosine, sine of kx minus omega t, and the second partial derivative of y of xt with respect to x is here would be minus k square a cosine of kx minus omega t. Alright, so because here we're talking about distance, remember that now this second derivative is the curvature. So this is the curvature. So we have acceleration and curvature. So here we have minus omega square of a cosine of kx minus omega t. So this is the same as minus omega square times y of x t. And this is the same as minus k square times y of x and t. So now, what happened if we divide the, let me erase now. What happened first if we divide the second partial derivative of y with respect to time, second partial derivative of y with respect to time, like this, all this divided by the second partial derivative of y with respect to x, like this. So we will obtain this was the acceleration, that is minus omega square of y of x t divided by the curvature, that is minus k square of y of x and t. Oops. So now we can cancel this and we have minus omega square divided by k square, minus omega square divided by negative k square, so it is just omega squared divided by k squared. Now, remember what was k? K was 2 pi divided by lambda. Alright, so k squared is 2 pi, is 4 pi, well, it doesn't matter, 2 pi divided by omega, 2 pi divided by lambda. And what was omega? Omega, that is the angular frequency. This is 2p times the frequency. So, I have k over omega. K over omega is, because on the other way, omega over k. Omega over k. This is 2pf divided by 2p all over lambda. Here, remember, I have the convenient one. So, I have 2 pi over 2p f lambda divided by 2p. So this is just f times lambda. And remember this, f times lambda is the velocity of the wave. So omega over k is the velocity. So here we have that all this is equal to the square velocity. So we can arrange this thing, and we can, if we want to find this, let me put this alone. Remember, I would need to send this. Let me put it here. I have equal to square the velocity. So I send this here and this here, and so I have that the second partial derivative of y with respect to x is equal to 1 over the velocity squared times the second partial derivative of y xt with respect to time. So I have that the curvature is equal to 1 over the square of the velocity of the acceleration of y. This is the wave equation, and is the most beautiful equation on physics, because it's seen on many topics. This states that when we have a positive curvature, that is when this is greater than 0, this is always going to be positive, so this would be greater than 0. So when we have a positive curvature, we have a positive acceleration, and when we have a negative curvature, we have a negative acceleration. And when we have a inflection point, that is when the curvature is 0, the acceleration will also be 0. So this is the wave equation. Now in future videos we will talk about the changes that we will see on a longitudinal and transverse wave, but this equation of the wave is representing both types of wave, the longitudinal and the transverse.